in the next subsection, we want to look at the first non-trivial algorithm to find strings, string patterns in a text. And we'll use finite automata for this. Now, I asked you to tell me what you know about these topics. And it seems either many of you love emoji or you haven't had an automata course. So I'll keep the references to all this a bit short, but at least you will learn something in this lesson that's useful. And there's also a substantial fraction of the people who've seen that before, but might have forgotten a bit of it. For those, it's a nice refresher then. So in essence, what this subsection is as you ask me a practical question, find this pattern in a text, and computer scientists or theoretical computer scientists tell you, well, this is something we know how to do. Listen, here's how to do it. Theoretical computer scientists talk about languages, formal languages, which are just sets of strings. And you can write formal languages, for example, like this. You can say this is the language of all strings that have something. Sigma star is an arbitrary string, arbitrary length. Then the pattern, and then another arbitrary string. And now you're asking if your text is part of this language. So you can formulate it in this string matching, in this deciding whether a string is part of a formal language. You can formulate the same question in this problem. Now, moreover, this language on the right, this sigma star p sigma star, is a regular language, in case you've heard this before. So in particular, you can describe it as a regular expression, which this kind of already is, depending on the notation you allow. And it also means whenever a language is regular, there exists a deterministic finite automaton to recognize it. So we can just simulate this automaton feeding the text through. And so in n steps, this tells you if the pattern occurs or not. That's really cool and pretty opaque if you haven't heard about all these concepts. So theoretician says job done, but programmer says hold on a sec. There's a few problems you glossed over. And the first one is not a serious one. You can fix that one. But the second one is a little more serious. We say in this step, there is some automaton, but that's not enough to program it. You have to find it. You have to explicitly construct it. And there is a way to do that, but it can't produce automata that are exponential in the length of the pattern. That's kind of a problem. We don't want that. That's really expensive. Now, let's ignore those two problems for a moment and see why, despite these problems, the approach actually works. It's just not completely obvious, even from the theoretical perspective, without looking at it closer, why. But let's assume first, let's make a visit to wishful thinking land. Let's suppose we already have an automaton that solved this problem for us. How would that work? Or formulate it differently, if you've never seen automata, now is the time to wake up, because I'll tell you what they look like. And so here is one. This is a deterministic finite automaton, abbreviated as DFA. There are these little diagrams with states and arcs. They have a starting state, that's where the arrow points to, that comes from nowhere. And then they have a bunch of states, which are just these circles. And the automaton at every point in time is in one state. And as the arrow suggests, initially we start in 0. A second feature, the states can be like these, which are with just a single line. These are non-accepting. If you read the string left to right, if you read the string through and you stop in a state that is like this, then you reject the string. And if you stop in a state with the double line, you accept the string. Now, automata, what does it mean, accept and reject? They're devices to tell you if a string is part of a language or not. And remember, we'll use this on this language. So the automaton will tell you if the pattern occurs or not by accepting or rejecting the text. That's how this works. Now, what I haven't told you is how the automaton runs. And I think let's just do this on an example. This is actually quite intuitive. We start in state 0. That's shown in this table down here. And now I'm reading the first character of my text. And well, here it happens to be an A. Then I look at my state and check the outgoing arcs, and there must be exactly one with an A. In a deterministic finite automaton, there's always exactly one outgoing edge with a letter for each, well, there's one outgoing arc for each letter in the alphabet. Now, one violation is allowed. If there's no arc, then you go to an implicit garbage state that you can never leave, which means if there ever is no arc for your letter, you're immediately reject because you're trapped in this doomed state. We don't draw those because sometimes automata have tons of arcs going to this garbage state, so that would clutter up the picture. But that's the only exception. What is never allowed is having two outgoing arcs with the same letter. All right. So from 0, there's an arc to 1, so we are in state 1 now. If we read another A, we follow this arc, so we are again in state 1. Now we read a B, that brings us to state 2. Now we're in state 2, we read an A. Where do we have to go? Straight. We follow this one. From V3, a C brings us back to 0. From 0, an A is back to 1, and we stay in 1 with another A. 1 with a B brings us to 2, then A brings us to 3, and now we go forward to 4, and actually 5, and 6, and 7. And here we stay with whatever letter, we just stay in 7. So the automaton has accepted the text, which means there was a pattern occurrence somewhere in the text. But what this doesn't immediately tell us where the pattern occurred. But if you pay close attention, the first time you reach state 7 signals the end of the first occurrence. And after that, we just stay in 7 forever. So it's not very interesting. And so you can calculate back from this, you know how long the pattern is. So it must have been at this position, whatever that is in the text. You can keep track of the index in the text. Okay? That's how a deterministic finite automaton works. And this automaton magically does the job in that whenever I feed it with a text that contains this pattern, it will end up in the accepting state because you basically march down to the right through the states. What's not obvious is if you take any of the other arcs, it will not mess things up. You will also find any occurrences that come later. But we'll come back to this. So here's that in nice again. So why does this automaton work? And how can we possibly construct this if it's not already given to us? The key insight is this in the box, and it might need a second to digest. So it expresses what a given state expresses in knowledge about the text. It means if we're currently in state Q, that means the text ends with a prefix of the pattern, namely up to the qth position, but excluding that one. And also there's no longer prefix of the pattern that we have seen up to this point. Okay? So the state number is the length of the longest prefix of the pattern. That's a suffix of the text we've seen so far. Anyone followed? I hope this is somewhere written here in roughly the same way. Well, this is maybe the shorter way to express it. Now, why is this enough to determine if we find a pattern occurrence and how to do the next step? Because this is just saying we can somehow guarantee this invariant that we always keep track of the longest prefix of the pattern that we've seen. But we don't know what the text looked like before this occurrence. So how can we keep track of this invariant? So if we find the next character and it matches, then we just make Q1 bigger. That's easy enough. That is why we have these edges to the right whenever we find the next character in the pattern. So for example, if we're in state 3, it means we have seen the first 3 characters of the pattern, which is ABA. We don't know what the text was before, but this is where we currently are. If the next character in the text now is a B, that happens also to be the 4th character in the pattern. So we just go to state 4, expressing the new knowledge that the prefix of P is now 1 longer. The interesting case is when the next character is not the right one, not the one that the pattern has. So like in this case, in state 3, the C, and here C is for an arbitrary character. What we know about the text is it ends with this prefix of P and this one new character. We also know that this is not a prefix of P because the C doesn't match. Okay. And the third thing we know is without this C, this was the longest match, the longest prefix of P that we could find. So in pictures, that's what the text looks like. In this situation, we have this prefix and the new character. Now what we try to find is a new state, which again is the longest prefix of the pattern. So we want to shift the pattern to the right so that now we again find a partial match. And the good thing about this is it only needs the portion of the text that we know. It is irrelevant what's to the left, because we only ever shift the pattern to the right. So we can, intuitively, we can just go through all the possible choices. We can shift the pattern by 1 and check if all the characters aligned match. If not, we shift 1 further, and so on and so forth. If we do this in our example, we have, so this was the case that, okay, let me leave this one. So we go to state 4. But then the other option was, if I have ABA and now I read a C, there's nothing in the first few characters of P with a C. So if I find a C in the text, I know there's no occurrence of P containing any of these positions. I have to shift the pattern entirely to the right. So the earliest occurrence can be starting after the C. And that's why I go back to state 0. The longest prefix of the pattern I can have seen at this point is empty. There's no way I can start with a C. Okay? So the important message is that this new longest prefix is always shorter than the previous one. So all the information we need is contained in what we know about the text so far. What we haven't figured out yet is how to efficiently find this, this next transition.